The management team at MiroCBT has developed and patented advanced processes for producing amino acid chelated minerals and selenium-enriched yeast with selenium concentrations of up to 5,000 ppm. Our company is the only one in the world with a patented process capable of producing selenium-enriched yeast at this high concentration. These innovations reflect MiroCBT's commitment to advancing high-quality, bioavailable supplements that support health and wellness. Minerals are essential for the proper functioning of living organisms. They provide structural support for bones, influence muscle and nerve function, and are key components of hormones and enzymes. Additionally, certain minerals play a critical role in supporting the immune system, where deficiencies can increase susceptibility to infections and contribute to chronic diseases. Ideally, all required minerals are obtained through the food chain. Plants absorb inorganic minerals from the soil and convert them into bioavailable organic forms for humans and animals. However, intensive agricultural practices, including the repeated use of the same soils without balanced mineral replenishment, have put a growing number of individuals at risk of mineral deficiencies. To address this imbalance, mineral supplements are commonly used in food products. The bioavailability of mineral supplements depends largely on their form. In the 1980s and 1990s, research showed that the bioavailability of some inorganic minerals can be less than 1%, while amino acid chelated minerals can achieve bioavailability levels of up to 95 to 98%. To address the issue of unbalanced selenium intake, an essential mineral that is part of 25 selenoproteins, inorganic selenium salts were initially used as supplements. However, the toxicity of these salts prompted the search for alternative selenium sources. It was discovered that baker's yeast can convert inorganic selenium into organic forms. The primary component of selenium-enriched yeast is selenomethionine, a natural amino acid that acts as a key antioxidant in many organisms, including humans. Gradually, metals in the form of amino acid chelates and selenium-enriched yeast have started replacing their inorganic counterparts, partly due to regulatory restrictions on certain inorganic forms. For example, in 2019, the European Union decided to ban the use of zinc oxide for weaning pigs, a regulation that took effect in June 2022. In contrast, zinc oxide remains a primary ingredient for zinc supplementation in Canada and is commonly used in various nutritional products for both children and adults. Particular attention was given to zinc intake in the early stage of the COVID-19 pandemic, when the EVMS COVID-19 Intensive Care Protocol of March 31, 2020, emphasized the importance of zinc intake in chelated form for disease prevention, mildly symptomatic patients, and patients with respiratory symptoms. Subsequent research indicates that low zinc levels can impair the immune response to COVID-19 vaccination, even post-vaccination. An analysis of over 1,200 articles by the College of Allopathic Medicine and the Department of Internal Medicine at University Healthcare found that zinc treatment was associated with reduced mortality rates. To this day, zinc supplementation remains important for those over 60, pregnant women, and individuals with medical comorbidities, due to the spread of new COVID variants, XEC and FLIRT. Amino acid chelated minerals. In 2011, the principal of MiroCBT patented a technology for producing pure amino acid chelated minerals for both humans and animals. During 2018 to 2019, pilot plant testing of this technology was conducted. The production line consisted of several key stages. Water purification station, tap water was brought to a suitable quality for the technological process using membrane filtration and reverse osmosis. Synthesis. The synthesis of amino acid chelated minerals was performed in a reactor, following the patented process designed by the principal of MiroCBT. Filtration and drying. After synthesis, the reaction mixture was filtered in the filtration unit and transferred to the spray dryer to obtain the product in powder form. Granulation. Following the drying process, the powder should be sent to the fluid bed granulator to be transformed into granules. Powders can be challenging to handle in many industries due to their loose packing, lack of uniformity, and poor flowability during transport. Granulating the powder improves its density, flowability, and uniformity, making it easier to work with across various applications. Pilot plant testing, preliminary results. During pilot plant testing, amino acid chelate minerals were synthesized in a custom-designed 77-liter reactor. Following synthesis, the solution was filtered, and a control sample was spray-dried at the University of Alberta's Agri-Food Discovery Place. This process yielded 266 grams of solid material with a crystalline water content of 4.8%, derived from drying 1 liter of solution. Based on this outcome, the mass of amino acid chelated mineral in the powder was calculated at 253 grams, theoretically comprising 48.3 grams of zinc, 97.5 grams of aspartate, and 107.2 grams of lysine. Analytical testing for metal concentration was performed by SGS using the ICP-MS method, while an SGS subcontractor measured the amino acid content of the chelated minerals. The zinc concentration in a twofold diluted sample averaged 45.4 grams per liter of solution, approximately 94% of the expected concentration based on the mass of the dried sample. However, the analysis of the undiluted sample showed a lower zinc concentration than the diluted sample, suggesting that dilution improved analytical accuracy. For amino acids, the final solution's aspartic acid concentration was found to be 22.5 grams per liter of solution, or 23.1% of the expected value based on the dried sample's mass. Lysine concentration measured 30.4 grams per liter, representing 28.4% of the expected amount. According to SGS, the total dried chelated mineral mass was expected to be 98 grams per liter of solution, in contrast to the 253 grams per liter indicated by dried sample data. During analysis, hydrolysis was used for amino acid chelate measurement, but, as with protein hydrolysis, this process may cause amino acid loss. Unaccounted loss can lead to underestimation, likely affecting final product analysis. The yield of zinc amino acid chelates in the 77-liter reactor reached 82% of the theoretical yield, which was lower than the 96% yield achieved in laboratory experiments. This difference likely stems from variations in experimental conditions. The patented synthesis technology for chelated minerals requires simultaneous heating and stirring, a process that worked well in lab tests. However, Hull Electric Limited installed a 30-amp cable and switch on the panel, while the 77-liter reactor specifications require a 50-amp input switch to enable simultaneous heating and mixing. During the court hearing, case number 2159630, Hull Electric Limited versus MiroCBT Limited, Hull Electric testified that the actual power required by equipment can vary based on operational dynamics, including components functioning at different times, and that in some cases, a lower-rated cable and breaker could be adequate. In paragraph 144 of the judgment, Judge Malfair concluded that the work was appropriately executed and no deficiency discount was warranted. As a result, heating and stirring were applied intermittently in the 77-liter reactor, deviating from the patented synthesis process for chelated minerals. Without on-site analytical equipment, the reaction duration was estimated based on laboratory protocols. Work plan for continuing pilot plant testing. 1. Electrical feed setup. Perform electrical setup for all equipment according to their technical specifications to prepare for synthesis operations based on patented amino acid chelated mineral production technology. 2. Synthesis parameters adjustment. Adjust synthesis parameters for producing amino acid chelated minerals in the 77-liter pilot plant reactor to match the yield obtained in laboratory conditions using a 1-liter reactor. This step ensures scalability to industrial production. 3. Optimization of drying process. Optimize the concentration of the amino acid mineral solution by pre-evaporating water to speed up the drying process. This should reduce evaporation time without increasing the solution's viscosity to the point where it cannot be pumped through pipelines from the concentration apparatus to the spray drying apparatus. 4. Granulation optimization. optimize the granulation of the chelated mineral powder obtained via spray drying. Industrial process flow diagram. The process begins with the purification of tap water using a reverse osmosis system. 1. The purified water, along with metal hydroxide or carbonate and amino acids, is added to the reaction vessel. 6. To initiate synthesis, the reaction mixture is continuously stirred and heated to the required temperature by introducing steam into the reactor jacket. Temperature and stirring conditions are carefully maintained throughout the process to ensure optimal synthesis. Progress is monitored by measuring the concentrations of metal, nitrogen, and carbon in the solution, which should match the target ratio in the final chelate. Once synthesis is complete, the reaction mixture is cooled via water circulation through an integrated spiral heat exchanger within the reactor. 6. The cooled reaction solution is then transferred to a filtration unit. 7. To separate any unreacted solids from the chelated mineral solution. The filtered solution is concentrated using a 3-body evaporation unit consisting of evaporators with natural circulation, with a coaxial heating chamber, and boiling of the solution in pipes. The filtered solution from the filtered solution tank, 9, is fed by a centrifugal pump, 12, to the heat exchanger, 10, where it is heated to a temperature close to the boiling point, and then to the first apparatus of the evaporation unit, 13. Preheating the solution increases the boiling activity in the evaporation apparatus. 13. The first apparatus is heated by fresh steam. The secondary vapor formed during condensation of the solution in the first apparatus is sent as heating vapor to the secondary apparatus. 15. Partially condensed solution from the first apparatus also enters here. Similarly, the third apparatus, 17, is heated by the secondary vapor from the second apparatus, and the solution entering from the second apparatus is concentrated in it. The spontaneous flow of the solution and secondary steam into the subsequent apparatus is possible due to the overall pressure difference, which arises as a result of the creation of a vacuum by condensing the secondary steam of the last apparatus in the evaporation system's barometric condenser. 20. The specified pressure is maintained by feeding cooling water and removing non-condensable gases with a vacuum pump. 19. The mixture of cooled water and condensate is removed from the condenser via a barometric pipe with a water seal. 21. The concentrated solution circulating in the third apparatus is fed by a centrifugal pump. 22, into the intermediate tank of the evaporated solution. 23. The condensate of the heating steam from the evaporators is removed by means of condensate drains. 14, 16, 18. The concentrated solution is then sent to a spray dryer, 24, where it is transformed into chelated mineral powder. Finally, the powder is processed in a fluidized bed granulator, 25, to produce amino acid chelated mineral granules of the desired size. Our company has yet to advertise its products, but we have already received inquiries for the supply of amino acid chelate minerals and selenium-enriched yeast. Our pilot production line for amino acid chelate minerals currently has a limited capacity of 10 kilograms of dry product per 8-hour shift, amounting to approximately 750 kilograms per month when operating 3 shifts daily. Unfortunately, this capacity falls short of meeting the demand of even a single potential international customer, though it may suffice for some local customers. Thank you for watching. If this presentation has caught your interest and you would like to invest in promoting our products in the market, we would be happy to provide you with additional information. Please feel free to contact us.